Howdy, this is your friendly neighborhood physics teacher here, and I had a few questions over Newton's second law. So we're going to go through the basics of Newton's second law and then do a couple of practice problems. We'll do basic and then we'll get into a little bit more detailed ones. So basically what Newton's second law is the equation that you've learned since 5th or 6th grade. Your force equals your mass times acceleration. That is Newton's second law. It's a relationship between force and acceleration. Now, we're going to take it a step further, and we know that more than one force can affect an object. So we're going to say the sum of the forces equals the mass times acceleration. This little funky E is a Greek letter epsilon, and it means sum of. And so then it's just anything that's behind it. In this case, it's an F, which stands for forces. So sum of the forces. And there we go. So that's basically what Newton's second law is. If you look on your formula chart, it's actually written with acceleration, solve for acceleration. This is on your formula chart, but the way that we use it 90% of the time is just the F equals ma. Now, just like in projectiles, we have to break it down into its x and y components. So you have to find the sum of the forces in the x direction. You have to find the sum of the forces in the y direction. And if you notice, I just labeled your forces and your acceleration. Your force is a vector. That means it has a magnitude and it has a direction. That's why you're able to represent it with an arrow. So you can have a positive and negative in front of the number. Same thing with acceleration. It's a vector. But your mass is a scalar. It doesn't matter if you're on Mars, Jupiter, Earth, whatever. It doesn't matter. Your mass stays the same. So you have to, just like in projectiles, it's nothing new. We're going to have to do this every time to break it down into its x and y components. So what does that look like? We're going to do like a little example here real quick. We have a box. We have a force going down, force going up, force going to the right, and a force going to the left. Now remember, magnitude matters. So hopefully you realize by now, if there's a force going down, it's going to be your force of gravity. If you're on a surface and a force going up, that's going to be your force of normal, or force that's perpendicular to the surface. We're going to make this force applied. We're going to make this force of friction. So now we're going to break it down into its x and y components. So we're going to focus on the forces in the x direction equals our mass times our acceleration in the x direction. So what forces are in the x direction? X means horizontal. So we have a force applied and a force of friction. Now remember, direction matters. So our force applied is positive direction. So it should be a positive number. Plus sum. I'm going to add up all the forces. And then our force of friction is pointing to the left, so it's a negative force. Equals our mass times our acceleration in the x. So that'd be our equation for forces in the x direction. Let's talk about our forces in the y direction. That's anything that's vertical. So our forces in the y direction would be our force of normal. Again, that's pointing up, so that's a positive direction. Plus our forces that are pointing down, which would be force of gravity, which is a negative direction. And that just equals our mass times our acceleration. So this would be the equation we use to solve for anything in the x direction. This would be the equation we used anything in the y direction. Now don't forget, you can take it a step further with your force of gravity. Force of gravity has its own special little equation, and which is your force of gravity equals mass times acceleration of gravity. Again, this is on your formula chart, just written with your g. So it is on your chart. It's written again with acceleration. Solve for acceleration, and you can manipulate that equation to solve for mass. So, but yeah. And yes, force of friction has its own special equation, but we won't necessarily deal with that in this setup. So that's kind of the basics of your Newton's second law. Now, a few things. Again, your forces in the x can't interact your forces in the y. So let's say we have an example like this. And you're going to pull a box. You're just going to pull a box. But in this case, you're pulling it at an angle. And let's say your force applied is 40 newtons. You're pulling it at an angle. We'll say the angle is 30. You still have to do your free body diagram. So we still have a force of gravity. We still have a force of normal. Now your force of normal is not going to be equal to your force of gravity anymore, because we have a force going up. It's being pulled, so we do have a force of friction. So this would be your free body diagram. It has the forces that are acting on the box. Sadly enough, though, this isn't useful for us because we have a force that's at an angle. It's moving in both the x and y direction. So we have to break that down. Where were you before I changed? Okay. So we have to break it down into force applied in the x and force applied in the y. This is your force applied, and we know that our angle is theta, which is just 30 degrees. Using your formula chart, we know that this is C, this is A, and this is B. I'm using what's on the formula chart. So we are going to have to use sine and cosine. So let's use sine first. We know sine of theta equals RA over B. Sine, our theta is 30, equals our A, which is our force applied in the Y, divided by our C, it should be C, not B. Sorry about that. Which is our force applied. We're looking for our force applied in the Y, so we need that by itself. So we're going to go ahead and multiply both sides by FA. And we get that our force applied times sine theta equals our force applied in the Y. And we're going to do the same thing with cosine now. Cosine theta is just our B over C. So cosine doesn't change, it's still 30, equals our B, which is our force applied in the X, divided by our force applied. Again, we're looking for our force applied in the X, so we're going to multiply both sides by FA to get that by itself. So we're going to do our force applied, cosine theta equals our force applied in the X. So now we know how much is in the Y direction, how much is on the X direction. So we can actually rewrite our little diagram here. Now, once we rewrite it though, it's no longer a free body diagram because it's supposed to be just the basic forces. Once you break it down to its X and Y components, that's not basic forces anymore. So we're going to have two forces going up. We're going to have our force of normal going up, and we're going to have our force applied in the Y, and then we're going to have our force applied in the X. So we can kind of see what forces are interacting now. Now we're able to break it down into our X and Y components. So what forces, there's a little in there. What forces are in the Y direction? So we have force of normal, which is a positive, so we can just leave that alone. Force applied in the Y, which again is positive. Our force of gravity, which would be negative because it's going down, equals our mass times our acceleration. So that would be our equation. Now, is it moving in the Y direction? Like if it says you have a box, you're pulling a box, the whole point is for it to slide across the ground. So are you trying to pick up the box? No. So in this case, our acceleration is going to be 0. So we can set this whole entire equation, our force of normal, plus our force applied in the Y, plus our negative force of gravity because it's pointing down, equals 0. So basically that's saying that everything pointing up equals everything pointing down. So force of normal points up plus force applied in the y points up equals the force of gravity, which points down. So there we go. Kind of have our force applied, our net force in the y simplified. So now let's look at our net forces, our forces in the x direction. So what forces are in the x direction? So we have a force applied in the x direction, which is positive because it's going to the right, plus a force of friction, which is negative because it's going to the left, equals our mass times our acceleration in the x. We can't do anything fancy with that because we know it's moving, we're pulling across the ground, so we can't simplify that very much anymore. So that would be the equation we would use to solve for that, if we were looking for our acceleration. So let's give some numbers to this. So I know y'all like numbers, even though AP Physics doesn't necessarily like numbers. That's why I'm breaking this down without numbers. But let's give some numbers into the mix. Now we can take it a step further because we do know what force applied in the x and force applied in the y is. So we could simplify it even more. So we'll go ahead and do that. So force of normal before we plug in numbers plus our force applied in the y is just our force applied times sine of 30. And that equals, and we know that our force of gravity has a special equation, which is just mass times acceleration due to gravity. So we can just do mass times g. There we go. So now it's broken down. Same thing over here. We can break this down even further. So we know that our force applied in the x, and how we're getting that information is basically up here. Yeah, we'll do that in the right color. Sorry. So it's our force applied cosine of our theta plus our force of friction. Now, yes, if we needed to break down our force of friction, we could. Okay. Equals our mass. Now we can, because we know our mass is just our force of gravity divided by our acceleration due to gravity. So we can plug that in. Times our acceleration in the x. So there we go. So we broke down the equations as far as we can. So now once we get the numbers, we literally can just plug in the numbers. And so this is where all the physics is happening, is manipulating the equations. But we can plug in numbers. There we go. So let's make our Force of gravity. We'll make our force of gravity 20. And now I'm just making up these numbers. So the last time I made up these numbers with the problem, I had to redo the force of gravity because I didn't make it strong enough. So we'll see if I guessed correctly this time. So force of gravity is going to be 20. Force applied is 40. And we'll make force of friction 5. Okay. So we need to solve for our acceleration in the x. So what we're looking for would be our acceleration in the x and our normal force. So that'd be what we're looking for. So there's no point of simplifying our force of gravity here because I gave us our force of gravity. So we could have just left it force of gravity since I gave it to you already. Okay, so let's just solve for our force of normal. So force of normal, we're leaving alone because that's what we're looking for. Plus, our force applied was 40. Sine of 30 equals our force of gravity, which is 20. Now, it is technically negative 20, but remember we brought it over to make it positive, so it's just 20 in this case. So now you just plug in 40 sine of 30 into your handy dandy calculator. And no, I did not make our force of gravity strong enough. Imagine that. Grr. We're jumping up to 30. Sorry, I was looking at the numbers. Sorry, I warned you. Making up numbers. Okay, let's try that again. So 40 sine of 30, that should give you 20. Come on. It's being contrary. Okay, let's try that again. Sorry about that. Equals 30. And then we're going to bring our 20 over. And we get that our force of normal equals 10 newtons. So if you notice, if I had left that at 20, we wouldn't have a force of normal. So that's why it couldn't stay 20. I made that a... There we go. So here we go. So we figured out our force of normal. Yay! we can do that again, just solve for our acceleration. So our force applied is 40. We have cosine of 30 plus our negative friction, which is -5, equals our force of gravity, which is -30 divided by, and we're just going to make G10, we're rounding. Yes, I understand that the acceleration due to gravity is -9.8. We're just rounding it to 10 to make math easier. And we're looking for our acceleration. So now we just kind of plug in. So we plug in our 40 cosine of 30. And I can't do that in my head. The reason I was able to do the 40 sine of 30 in my head, because sine of 30 is 0.5, but we can go to our thing here. So here, I'll just show you. So if we did 40 sine of 30, nope, we don't want radians, we want degrees. Let's try that again. So we want degrees. Okay. Okay. 40. Come on. 40 sine of 30 equals 20. See, there we go. Whew. And now let's do 40 cosine of 30. That equals 34.6. Let's go ahead and round that to 35, just to make math easier. So we're going to round that to 35 plus -5 equals -30 divided by 10. And negatives cancel out to 0, so it's just 3. We're looking for acceleration. 35 minus 5, it's just 30, equals 3 times your acceleration in the x. We're going to divide both sides by 3. And so you get that your acceleration in the x direction is 10 meters per second squared. So there we go. So again, each step isn't that bad. It's just a lot. It's just a lot of steps. But we're either just multiplying, dividing, adding, subtracting. The hardest thing is the sine and cosine, but that is on your formula chart. There's no need to memorize it. So that's something that you would see on the AP test. I'm going to do one more example that you definitely will see. This one is an interesting example. Our box is no longer on a flat surface. Our box is now on an incline. Force of gravity still points directly down. Our force of normal points perpendicular to the surface. And the box would try to be sliding down, So our force of friction would be pointing up the ramp. The reason I know my force of friction will be pointing up the ramp, because it's something on an incline. It naturally wants to go down. So if it's not moving or if it's sliding, your force of friction always goes opposite of the motion. Being the motion would be that direction. So again, this is our free body diagram. Nothing fancy, it's just that. But breaking it down to its x and y components can be complicated, because the frame of reference we mostly stay in is like this, right? And so the only force, so if we were going to put that into x and y planes, we have force of gravity, force of normal, and force of friction. So we would be breaking down force of normal and force of friction into its x and y components. So that's a lot of sine and cosine. But remember, frame of reference is relative. You can change your frame of reference. So we're basically going to tilt our head. So we're going to change our frame of reference to be that our x goes with the surface. And so therefore our y goes down. Because it has to be a 90-degree angle. So if we put our forces now on the x and y plane, our force of friction, we don't have to change. Our force of normal, we don't have to change. We only have to break down our force of gravity, which makes life a whole lot easier. So we just have to turn, basically, figure out how much of that force is in the x direction and how much of that force is in the y direction. So we're going to, just like how we did before, draw our triangle. So that's our force of gravity in the x. This is our force of gravity. And then we have our force of gravity in the y. The cool thing about doing this is geometry. So this theta and that theta is going to be the same. I can't remember the geometry rule on the top of my head, but just know that the bottom theta and this theta is going to be the same. This is actually going to end up being a 90-degree angle there. So again, this would be your C, this would be your A, and this would be your B. And you can figure that out if you tilt your formula chart where your theta is at the bottom. And you can figure out which one would be A and which one would be B that way. So you can also rewrite or redraw your little thing so you can see a little bit better. Now remember, this is not official free body diagram because it's not the basic forces, it's not the original forces. You have your force of normal going up. You have your force of gravity and the y going down. Now do a force of friction, pointing up the ramp, and you have your force of gravity in the X, pointing down the ramp. So what's making it move is your force of gravity in the X. So it's, yes, force of gravity is making it down, but it's not full force of gravity because of the ramp. So that's kind of like what we're using when we make our net force in the X and net force in the Y. So if we were going to solve for our force of gravity in the X, we would end up using our sine. So sine theta equals A over C. So sine theta would end up equaling our force of gravity in the X divided by our C, which is just our force of gravity. We're trying to get our force of gravity in the X by itself. So we get that our force of gravity sine theta equals our force of gravity in the X. We can do the same thing for our force of gravity in the Y. So our cosine would be B over C. So cosine theta equals our B, which would be our force of gravity in the Y, divided by force of gravity. Again, we just divide both sides by force of gravity because we're trying to find force of gravity in the Y. Then we get cosine theta equals our force of gravity in the Y. Now, because we know that our force of gravity has its own special equation, which is our mass times acceleration due to gravity, we can actually plug that equation in for it too. So we get that our mg cosine theta equals our force of gravity in the Y. And again, we can plug it in here. Mg sine theta equals our force of gravity in the X. And again, you might be saying why I'm doing that, because this is what AP wants you to do. It gives you your basic equations, and it wants you to kind of squish it all together. So now, let's look at some of the forces in the Y direction. So what forces are in the Y direction? Hopefully you said force of normal plus a negative force of gravity in the Y, which equals, and again, you can solve for mass. It's mass by itself. So our mass is force of gravity divided by acceleration due to gravity. So we can plug that in. If we need to. Just according to what we have. If we have force of gravity, we need mass. Or if we have mass, so we can plug that in. Times our acceleration of y. And again, is the box moving in the y direction? Is the box moving either in this direction? Hopefully you said no, it's sliding down. So your acceleration of y is going to end up being 0. So we get that your normal force plus our force of gravity in the y equals, we're just going to go back and put mass there, 0. 0 times anything is 0. So we get that our normal force plus our force of gravity in the y equals 0. So we can see that our normal force, sorry, we can go ahead and, let's go ahead and bring this to the other side. We see that our normal force equals our force of gravity in the y. And we know what our force of gravity in the y equals. We have that equation. So we can take that equation, and we can plug it in. Our force of normal equals our mass times gravity cosine theta. So there we go. That would be our normal force. Now what would be our, starting with that, let's look at the forces in the x direction. And let's solve for acceleration in the x. So what forces are in the x direction? We have force of friction, make that a little thicker so we can see a little better. So we have force of friction plus a negative force of gravity in the x. And again, that's heading to the right, so that's positive. It's heading to the left, that's negative, or that's up, that's down, either way you want to look at it. Equals mass times our acceleration in the x. So we can simplify our force of gravity in the x. We can plug that in there. So it'd be a negative mass times acceleration due to gravity sine theta equaling mass times acceleration due to acceleration in the x. Now, we now know that force of friction, and we could left it like that, figured out what we need to solve for, stuff like that. But we now know force of friction has its own special equation. Our force of friction is mu times normal force. So we can take that equation and plug it in. So that'd be mu times normal force plus mass times acceleration due to gravity times sine theta equaling mass times acceleration in the x. And we know what normal force equals. So we can plug that in. So we get mu times our mass times acceleration due to gravity cosine theta plus mass times acceleration sine theta equals mass times acceleration. Now, what happens when you have a variable in each little section? It can cancel out. So mass really doesn't matter. That's why I said you could plug in if you need to, but mass doesn't matter. So you can cancel out your masses. And you're left with your coefficient of friction times your acceleration in the due to gravity times cosine theta plus negative acceleration of gravity times sine theta, which equals your acceleration in the x. And there you go. There's your basic equation. And from here you can plug in. If you know your angle, we know that as long as we're on Earth, g is negative 9.8 or 10. And then we would have to know the coefficient of friction. So there you go. That is what a true AP question would look like. Again, hopefully that helps kind of explain your Newton's second law with some basic equations, simplified, what you see on your problem, getting into the more complicated ones. And hopefully that helped. Have a wonderful day. Remember, you're loved and appreciated. Bye.